Hello, everyone. Welcome back to Watershed Wise Landscape Professional Training. This is Module 8, Water Budgeting. And everything that we are going to talk about in water budgeting, you have seen before, because all of these formulas are things that we've talked about in irrigation scheduling. But now we're taking a twist. And the twist is that we're going to start to talk about water in the landscape as for the entire landscape, not just for a particular plant. So remember, in irrigation scheduling, we went through how to determine the plant water requirement. And you'll remember that that included asking the question, where are we? And answering it with ETO, which is a measure of evapotranspiration of a reference plant, cool season turfgrass, in a particular area, grown in a particular way. And so we took ETO and then we adjusted it for the particular plant that we had, because we probably didn't have the perfect grass, right, in the landscape. We have some other plant. And so we took that other plant and we compared it to the reference plant, and we did that with a percentage called a plant factor. And when we multiply the ETO by the plant factor, we end up with what's called plant water requirement. And then I hope that you remember, we actually adjusted plant water requirement for the irrigation distribution uniformity or irrigation efficiency that we had with the irrigation system in the landscape. So at the end of that exercise, we were looking at how much water does a particular plant in this place, in this landscape that uses this irrigation system require. And that helped us to determine actual water requirement, irrigation water requirement, and ultimately irrigation interval and total irrigation runtime. But now we're going to shift this to asking the question, how much water in gallons does my landscape need? Because plant water requirement was all in inches. Irrigation was all in inches. Now we're switching to how many gallons does my landscape need? And that means that we now have to be looking at inches per square foot. So we need to be looking at an area in order to come up with our gallons. And this is actually the way that we are most likely to be talking about water in a landscape, either with property owners or with regulators. It's rare that we have conversations about particular landscapes or particular places and talk about water use in the landscape in inches. It's only really if we're talking about precipitation specifically or irrigation applied that we end up talking in inches, and then it's going over most people's head. So most of the time, we're going to be talking about water use in landscapes in inches. And that means that we have to convert our data that is in inches into gallons. And this is actually extremely straightforward. The way that we convert our inches information into gallons is, first of all, we need to have an area of some kind that we're using, and let's imagine that we're using 1 square foot. So we're going to start our calculations at 1 square foot. So for 1 square foot, if we have X inches, let's say 1 inch of water on 1 square foot, how many gallons is that? And the way that we determine gallons is we multiply the inches per square foot by 0.62 gallons per inch per square foot. So 0.62 is the conversion factor, if you will, to go from square foot, inches per square foot, to gallons per inch per square foot. So gallons per square foot. And this is, you multiply by 0.62 only when you are trying to figure out an area of land, how much water is being used or needed or captured from this particular area of land. So let's do a quick example that you can see here on the slide. If we have an ETO in, well, actually, this is an ETO, but we have a plant water requirement of 3 inches per square foot in March. So it's a little tricky, right? Because now we have a month also, but we have that many inches. Well, okay, so we have 3 inches of plant water requirement and per square foot. So how many gallons is that per square foot? Well, 3 inches times 0.62 comes out to 1.86 gallons per square foot of landscape. So if I have 1 square foot, it's 1.86 gallons. If I have 1,000 square foot, it's 1,860 gallons. So this is essentially the way that we're going to start to be thinking about water budgeting and rainwater capture, because both of those calculations are utilizing gallons per square foot, or gallons per, it's not gallons per square foot as much as gallons for this area, for this surface area. So now we're actually switching out, we're adding to our way of describing our landscape. If you remember, in plant water requirement, we asked 2 questions. The first one was, where are we, right? And that's ETO. And then we asked, what's there in the landscape? And the things that were there in the landscape were the things that utilized water. So plants was one, and that's plant factor. And the other adjustment factor that we were looking for was irrigation efficiency. Now we're also going to ask ourselves, how big is this landscape? So how many square feet is it? And just anecdotally, I want to tell you that when you get facile with this type of calculation in your, kind of in your head, you have an idea of what ETO is in a particular area, a round number, and then in the places where you work. So you get that in your head, and you're out in a landscape, and you see that it's mostly, low water requiring plants. So you apply 20 or 30% to that number, and now you have a plant water requirement in your head. And you walk out and you see, oh, this is 1,000 square feet of area, or this is 10,000 square feet of area. And boom, right away you can say, wow, the landscape water requirement in this area is going to be X gallons, and people can't believe it. They can't believe that you can do that in your head. And it's really not that challenging. It's just being able to think about the components of it. So I ask myself, where am I located in ETO? What's there in this landscape? And I don't even include irrigation efficiency usually in these conversations, because, we're just, it scares people, because if I put irrigation efficiency in there, it would be twice as much. And then, how big is the landscape? And once we become facile with that, it becomes very easy to start doing these water budgeting and rainwater capture calculations. So essentially, just to reiterate, we're going to switch from just looking at plant water requirement, and now we're looking at landscape water requirement. And the way that we do that is we are adding the area, multiplying that by our plant water requirement, dividing by our irrigation efficiency, multiplying by 0.62, and that tells us how many gallons a particular landscape would require. So we have a bunch of exercises that I'm going to encourage you to go through. I'm going to go through the first little bit of this one, but then I encourage you to try them on your own. And really, again, this is just a matter of working with it. Something that I want to mention is that there are times when you're going to see landscape water requirement expressed in this formula that I call like a double-decker formula. So it's got a piece on top, and then it's got a piece on the bottom, and it actually looks pretty confusing. One of the cool things about multiplication and division is we can essentially align a formula into into a single line and multiply and divide across that line and come up with the same answer. So that's what we do here, is we've kind of made all of our calculations. We've gotten rid of the double-decker calculations. And now when we set them up in the same order, we can see that we're going to come up with the same answers as if we were trying to do it in the double-decker. So our formulas are all going to be lined up with the square footage in front, and then ETO times the plant factor, plant water requirement, and then divided by irrigation efficiency and converted to gallons at the end. Now, you can play with this if you want, see if you get the same answers, etc. This is a really good way to do it. And plus, you can write it out very, very quickly for someone on a sheet of paper, for yourself on a sheet of paper. And it allows you to start to compare, the landscape water requirements. And that's actually what we're going to be doing in water budgeting. All right, so in this particular landscape, we have an ETO of 47 inches, and we have a distribution uniformity of 70%. And we remember that in our world, distribution uniformity is kind of the driver for irrigation efficiency. And so it's a good proxy for irrigation efficiency. We're going to use it here because we have no other information about the irrigation system. We have two landscape areas that we're taking a look at. The first one is, and I'm just going to deal with the first one really, it's 1,000 square foot landscape area in a place with 47 inches and distribution uniformity of 70%. So if I were just approaching this, in a landscape, I would say to myself, okay, well, how big's the landscape? 1,000 square feet. Write that down. All right, where am I? I'm in ETO 47 inches. Okay, I multiply by 47. What's the plant here? Well, I look at the problem and I see that my plant is high water use plant. And it's not the perfect grass, right? It's a high water use grass. And I know that for high water use plants, my plant factor is going to be between 70 and 90%. So, and I don't have the slide rules, with me. So I just, I take the middle of the road, 80%. So my plant factor becomes 80%. And I've been given the distribution uniformity of this irrigation system at 70%. So I can divide by 70%. I multiply by 0.62, and that will give me 26,282 gallons per year. Very straightforward, isn't it? So if you do this exercise, it's just it's really kind of rote memory to just learn how to use the formula and to be able to very quickly come up with landscape water requirement. Now, one of the cool things about landscape water requirement is that you can take an entire landscape and then take a look at it and actually break it down into different hydrozones or different components. So let's imagine that you had a landscape, 1,000 square foot landscape, but it had 3 different hydrozones in it. It had one hydrozone that was a high water requiring one, and it had one that was medium, and it had one that was low. The way that you would come up with the landscape water requirement, because those are 3 different plant factors, right? And the areas are going to be different, maybe among them. The way that you come up with the landscape water requirement is you calculate the hydrozone water requirement of each area, and then you sum them, and that gives you your landscape water requirement. So, of course, the landscape water requirement is going to be different for different sized landscapes. That makes sense. When the delivery systems are different, the plants are different, the locations are different. So that changes ETO, plant factor, irrigation efficiency, and area. But it's still the same formula. And we are just going to do one very quick exercise just to hammer it in, because really you're all probably thinking, wow, that's super easy. What's this have to do with water budgeting exactly? Well, okay, you'll see in a second. Let's just be really comfortable with landscape water requirement. So how big is this area? Well, we're told in the exercise that it's a 50,000 square foot area, and the entire landscape needs to be redone. So this is an interesting little differentiation. You might be asked, and you really have to look at what your local ordinances and your local definitions are, but you might be asked, what is the total landscape area of a particular property? And in general, that describes the area that is going to have plants and irrigation, and especially is going to have irrigation. So it's going to require water. So it's possible that you would have a total landscape area. Like, let's imagine that there was a renovation that was going to be happening on a landscape. It's possible that you would have a total landscaped area that was higher in the beginning than it was after the renovation, because all of the hard surfaces would be taken out of the total landscape area. So just keep in mind, in your head that when we get into water budgeting, we're only looking at areas of land that require water. That's kind of an important little differentiation. So when you see total landscape area, make sure that you have the right information about the total landscape area in order to use that square footage in your calculation. So in this case, 50,000 square feet. And then we ask ourselves, well, what's there? What's in this place? Well, we have warm season grass, which we have a plant factor of 70%, and we have an irrigation efficiency of 50%. So we know right away that however much water this landscape requires from the plant factor, we're going to have to apply at least twice as much because our distribution uniformity is so low. And so now, what is the landscape water requirement? We need to know also, where are we? And we know that we are in ETO of 49 inches. So landscape water requirement is just setting it up. How big? 50,000 square feet. Where are we? 49 inches of ETO. And the plant, and then what's there? Well, the plant's warm season grass, 70% plant factor. And we divide by the distribution uniformity of the irrigation system, which is another ETO adjustment factor. And then we multiply it by 0.62. And so this particular landscape, hard to believe, but there it is, requires 2,127,000 gallons of water per year. Like, for what? Honestly. And this is the discussion that the designer had with the property owner when they were talking about a renovation for the landscape. Started out with this calculation to show them, and actually was able to tie it back to a water bill to see, yes, indeed, 2 million gallons of water a year are used by this landscape. So what happens if we were just to change that irrigation efficiency? Like, imagine instead of having these conventional spray nozzles, we changed them out to a rotary nozzle that had a better distribution uniformity or better irrigation efficiency. What happens to the landscape water requirement? Well, we plug in the 70% distribution uniformity to our formula. We're still in a place that has 50,000 square feet. We haven't changed location, so it's still 49 inches of ETO. We still have warm season grass at 70% plant factor, but now our distribution uniformity is higher. And when we convert to gallons, we find that our landscape water requirement has dropped. It's dropped from 2 million plus gallons down to 1,519 gallons per year. So we've saved 500,000 gallons of water per year on this landscape just by changing out the spray heads. And that's real water savings. So it's pretty easy to convince somebody to make that quick change, especially if they're about to go through some kind of a renovation, or they're making changes in incremental bits. So then this designer wanted to convince these people to take on a project where that grass would be removed and it would be replaced with very low native grasses and shrubs. And we know that in this particular place, our very low water requiring plants have a plant factor of about 10%. Now, because you've been through plant factor, you know right away, hey, this is going to be a big deal. This is going to change things really dramatically by changing out from the warm season grass at 70% to plants with plant factor of 10%. But of course, the property owners don't really know what to expect. So you sit down with the piece of paper and you say, all right, we save 500,000 gallons of water per year by changing out the irrigation system. Now let's talk about what happens when we do the plant renovation. And oh, by the way, you can see actually in the final design here that some of the total landscape area actually came out. We're still using 50,000 square feet here in our calculations. But it got even better because we actually removed some of that landscape area and put in permeable paving. But for the purposes of this discussion and this like sales technique, really, we just stuck with the same landscape area. So now, what is the landscape water requirement for the new landscape? Well, we're still at 50,000 square feet. We are still at 49 inches ETO, but we've changed our plant factor. So we're multiplying by 10% now. And then we divide it all by 70% because remember, we have the more efficient irrigation. We convert it to gallons by multiplying by 0.62. And voila, what do you have? Well, you end up with a landscape that only requires 200,000 gallons of water a year. We went from 2 million gallons of water a year to 200,000 gallons of water a year, just by rethinking how this landscape was going to be. And you know what we call that? We call that boom. That is a sale. That is like, this person's on board. These property owners get it now. They had no idea that, when other people came in and said, yes, we'll save you water, that was nice. But when you came in with your envelope and wrote down 3 little formulas on it and showed them how their landscape water requirement was going to go from 2 million gallons a year to 200,000 gallons a year, they're now on board. And it almost doesn't matter how much water costs to have that conversation. It's great because when you start working with the actual water cost, you realize, wow, this is real money, because people who are putting 2 million gallons of water a year into their landscape are in high tier water pricing in most places. So when you pull that down to 200,000 gallons of water a year, they change their tiers even, and it has a multiplier effect on the reduction of their bill. So this is really the essence of the water budgeting conversation, is to be able to manipulate the plant factor and the irrigation efficiency of the landscape, make changes to those two things in order to create a landscape that is only going to require the amount of water that you're allowed. So that's where we're going to go, is into this comparison of how much water is my landscape requiring given all these changes, and how much water am I going to be allowed to utilize. So you will remember that we talked about hydrozones briefly, but hydrozones are a really important concept in landscape water requirement, because when we group our plants together for their water type, it makes it, well, first of all, this is really the only way that we can create an irrigation system that's efficient, is by having the plants that have the same water requirements together. And it's also the way that we then develop the total landscape water requirement when we have plants that have different plant factors. And the way that we group plants together for hydrozoning, it's also a little bit of art, but we start with the water use. So grouping them by water requirement. Are they moderate, low, very low, or even high water requiring? And then there are other ways to group them together. So one thing might be by root depth. A good hydrozoning practice, especially in times of drought, is to prioritize deep-rooted plants that are taking a long time to grow, like trees and large shrubs. And so putting those plants onto a separate hydrozone, irrigating them separately, putting them on a different valve zone, and then having them be calculated separately in landscape water requirement can be very beneficial, because you can show the value of putting water on those plants. And if for some reason water is going to be restricted, you can make the case that those plants are the ones that you should be putting water on, and you are in fact saving water because you're not putting water on these other plants. So there are a bunch of different ways you can hydrozone, but the most important way to hydrozone is by water requirement. And then those hydrozones will resolve themselves into valve zones. So in your landscape, you're going to have different irrigation valves controlling the water going to the different hydrozones. Now, what happens when you have a mixed hydrozone? How do you evaluate it for landscape water requirement? It's a bit of a challenge, because if you have a mixed zone where there's some moderate water use plants and there's some low water use plants, what do you do? Well, the thing is that it's our belief that, and again, your local municipality may give you very specific guidance on how you handle a situation like this. But in the absence of that guidance, if you were just thinking about how we're going to use this way of calculating and thinking, we should have our own kind of internal rules. And the rule that we utilize is one of being conservative, essentially. And so we want to overestimate the amount of water that a landscape would require, so that we are not in a situation where we where we don't have enough water, if we're having to make a deal, for the amount of water we're getting on the property. So if we have a mixed zone where we have, let's say, moderate water use plants put together with low water use plants, and they're being irrigated by the same irrigation zone, that hydrozone is going to be calculated and viewed as though it's all the higher water requirement. So in a place where you're given plant factors, you're given that information, you're not using slide, because remember, in slide, almost everything is 80% or 60% or 70%, right? It's like they're all the plants. It's based on form instead of really the water, an assessment of water use, high, medium, and low. It's really just based on form, unless you have your native plants, which are 30%. So what happens if you have a mixed zone of non-native plants at, let's say, 70% and native plants at 60%? What do you do for that particular zone? It's all being irrigated the same. Well, you choose the higher plant factor is the one that rules for that hydrozone. And the reason for that is it's a more conservative way of looking at the water in your landscape. You're overestimating in some ways the actual amount of water that your landscape would require. But the truth is that if you had to water to the health of a plant in that zone, that mixed zone, you would probably be watering to the health of the moderate plant. So it isn't totally unreasonable to imagine it. And yes, there are going to be some managers that say, hey, I let my moderate plants get stressed. It's okay. I water to the low water. That's fine. That's a management thing. But when you're estimating how much water a landscape is going to require, you go with the higher number in a mixed zone. So the plant factor of the highest water use plant in the zone is what's going to dictate the plant factor for the entire hydrozone. What if the hydrozone is a water feature? Now that's a really interesting question, because if you go to the EPA water budgeting calculator, you'll see that the plant factor on a water feature is 80%. I cannot figure out why. The only thing I can imagine is somebody with the pool industry was really effective in arguing that an open body of water evaporates less than 100%. Can't really figure that out. So I guess what is being argued is that a water feature is equivalent to the high water requiring plant, and a high water requiring plant would be 80%. So maybe that's where that logic comes from. But for us, and in the absence again of guidance, it is much more conservative to imagine that an open body of water would be evaporating at, not even evapotranspiring, right? Evaporating at a rate of 100% of ETO. So when you have a water feature in your design, you're going to assign a plant factor of 100% to it. And is there a distribution uniformity there? No, no distribution uniformity. It's just plant factor. So it's, and you could say, okay, it's distribution uniformity of 100%. So your plant factor is 100%, your distribution uniformity is 100%. Essentially, a water feature hydrozone is going to be the area of the hydrozone, the square footage of that hydrozone, times ETO times 0.62. That's going to tell you how many gallons that water feature would require over the period of time. And this is really what a plan with hydrozones looks like. When we're doing design work, when we're evaluating a landscape, and not even doing design, but just evaluating it, trying to determine, how much water would this landscape require. Again, making a kind of color-coded plan, I find to be really, really helpful, because it shows us if we have, do we have hydrozones where we have a mixed zone of moderate water use with low water use, or whatever. Now, a lot of people will argue, and I think effectively, and it's really up to you, and it's up to your local municipality's ordinances about how to handle this. But a lot of people will argue that when you have very low water requiring plants with low water requiring plants, the differentiation is not as drastic as it would be for moderate water use plants with low or very low. I'm going to leave that to you. Maybe it's okay to mix those things up and you make up for it in the way that you irrigate it. But from an analysis point of view, I would still go with the highest plant factor of a mixed zone and just be conservative. All right, so let's put this to sort of practical use. You're in your car and you're driving by a landscape, and someone says, "Oh my gosh, look at these green landscapes. I mean, we're in a drought. Like, how much water do these landscapes possibly use?" What do you do very quickly? Well, you know where you are. So you have you have your ETO in your head. Let's say Escondido, or pick a city but it's a place that you work. So you have a plant factor in your head. Let's say 50 inches a year. You drive by, it's 1,000 square feet. You can see very clearly that it's a cool season turf, so it's really close to the ETO plant, and it's lush weed-free lawn, so it must be very close to the ETO plant. And that's a high water use plant. Boom, you come up with your calculation very quickly. Take the square footage times the ETO times the plant factor. As you're driving by, you don't really need to think about distribution uniformity, but you can, and that works. Now, what about so that drive-by is very much like imagining that. So I'm moving now to water budgeting. This is essentially saying, how much water am I going to allow you to have on this landscape? Am I going to allow you to have 100% of the water that this landscape could have, like 100% of ETO? Is that a reasonable amount of water for you on this landscape? Maybe, and that's what that drive-by really is. It's like kind of looking at it like 100% of ETO, like a real quick idea of how much water that landscape would require if it weren't really adjusted by plant factor or by plant factor or distribution uniformity. So when we're talking about water budgeting, we're going to start with the concept of how much water could this landscape be allowed? Well, 100% of ETO is possible. And in this particular case, we have a landscape with 1,330 square feet, an annual ETO of 49 inches. And we're imagining that it's going to be allowed to have 100% of the water of ETO. How much water is that? That's 40,405 gallons of water per year. Now, what have we really done here? What we've done is we've taken the plant factor and the irrigation efficiency, and we've kind of turned it into a adjustment factor, a budget adjustment factor for ETO. So we kind of separated out plant factor. Here we're saying it's 100%, and we're dividing it by irrigation efficiency, which we say is 100%. So it's one equal to 1 when we put them together. But those two things together have become an adjustment factor onto ETO that is going to allow us to quickly say, okay, this is how much water I would be allowed on this landscape if I were allowed 100% of ETO. But what if I wasn't allowed 100% of ETO? What if I was only going to be allowed 40% of ETO? Well, that is the essence of a budget, right? I can't get 100%. I'm only going to get 40% or 50% or some percentage, some adjustment factor of ETO. What I am going to have to do in order to create a landscape that meets that water budget is I'm going to have to manipulate my plant factor and my irrigation efficiency and manipulate those two things in order to create a landscape that's going to meet the budget. So here we had our 40,405 gallon landscape that was 100% of ETO, but I have a water budget that says I need to adjust ETO by 40%. And so now I'm really only going to be allowed to have 16,000 gallons on this landscape. That's all I'm going to be allowed. The question is, did my design that I have actually comply with that budget or not? Well, the way I assess that is I now do my landscape water requirement with the new landscape. So the water budget is there. It's Square footage times ETO times the adjustment factor times 0.62. That's how many gallons I'm going to be allowed to have. The maximum amount of water I'm allowed. And now I'm going to figure out, does my design actually comply with that? And so now I'm going to do landscape water requirement. It's one hydrozone. I take my square footage, I multiply it by my ETO, multiply it by my plant factor for the zone, divide it by my distribution uniformity, multiply by 0.62, and that's going to tell me the estimated total water used by this landscape, or my landscape water requirement in this particular place with this particular landscape. Is my water budget higher or lower than my estimated water requirement? I'm going to compare these two things. My estimated water requirement is only 9,000 gallons. My budget is 16,000 gallons. I'm good. I'm good. But what if I had spray irrigation here in the new landscape instead of drip irrigation? And you know it was drip irrigation, right? Because you can see that the distribution uniformity is 90%. So it's very likely to be highly targeted irrigation, drip irrigation. So what would happen here if I had irrigation that was a conventional spray? Would my estimated total water used, would it be higher than the budget? Most likely. So this is the thing that you essentially end up doing. You create the water budget based on a given ETO adjustment factor, a budget factor percentage. You calculate out what the maximum allowed water is going to be, water budget. And then you look at the landscape that you're given or that you're creating, and you calculate out the landscape water requirement. In this case, we're going to call it the estimated total water used. So that's the design plan, if you will, of the landscape. And you compare the two. If the water budget is higher than the design plan, you're in good shape. If the water budget is lower than your design plan, you now have to manipulate, you have to change things. You need plants with a lower plant factor. You need to get rid of a water feature. You need to change out your irrigation to something that's more efficient so that you can bring your estimated total water use down below your water budget. So estimated total water use is a real thing at WU. Hate it. We call it a design water plan, but you can call it whatever you want. Estimated water use of the landscape. It's just a landscape water requirement, really. And you will need to think about what are ways that we can reduce that estimated water use. And some of the things that you can do are hydrozone more efficiently. So if you hydrozone more efficiently, you would be able to get credit for areas that are low water use plants. You wouldn't be taking your whole mixed bed and utilize, using the higher plant factor on it. You would have some portion of that would be lower water use if you were hydrozone more effectively. You want to maybe think about, are there hydrozones that don't require potable water? Your local ordinances may actually exclude areas that do not require potable water, that are using recycled water or that are using other forms of gray water, or that are using rainwater. And actually, one of the most beautiful things that you could do is take an entire hydrozone out of the calculation because it doesn't have irrigation at all. It's running off of rainwater instead. So that's an idea for a way to actually reduce your estimated total water use. Shifting your plants from non-native, non-climate adapted plants to climate adapted plants will probably give you some benefit in the estimated total water use. Making sure that your irrigation system is as efficient as possible, because as your distribution uniformity rises and your efficiency rises, your estimated total water use decreases. Hey, creating living soil that acts like a sponge. This isn't something that you really get credit for in the calculations, but it's something that will help you in your management so that you can manage your water use to your estimation or below. And then, as I said, using captured rainwater. All right, so a little bit of a digression just for 1 second. We've already used this calculation in the course, but it's worth mentioning because when we do water budgeting, we almost always end up with a couple of water bills in front of us so that we can actually talk about how much water people are really utilizing at the time. And then we help them to compare that against a water budget so they can kind of see what they're going to have to do in order to match their water budget or get below it. So it's worthwhile for us to just remind everyone of the fact that most water bills are actually presented in terms of units or 100 cubic feet of water. It's rarely a cubic foot of water that you're seeing on a water bill. So a unit or 100 cubic foot is they're equivalent, and that is for if 1 cubic foot of water is equal to 7.48 gallons, then 100 cubic feet of water is equal to 748 gallons. So we're going to have at least a couple of questions that are, hey, your water usage is 10 units or 10 HCFs. How much water did you actually use? And you will know that you'll take the 748 gallon per HCF and multiply it by the HCFs used. So if it's 10, it's 7,480 gallons of water. That kind of thing. Pretty simple. But when you get to the level, this is not something that you're really talking to residential property owners, most residential property owners about. But when you start talking to people in agriculture, or you start talking to people in more commercial situations, and then of course regulators and managers of water on a wholesale level, they're talking about acre feet of water. And an acre foot is about 326,000 gallons of water. So a million acre feet is even something that you're going to read about when you hear about drought issues like on, in Mississippi River or in or Sacramento River, or Colorado, that you will hear about million acre feet of water. And so, it's a big number. Okay. And essentially this is an acre foot is 1 foot of water, 12 inches of water over an acre. That's pretty much what an acre foot is. Okay, so what can we do to reduce our estimated total water use? Or so I'm going to ask the question that's actually on the slide because it's a very tricky question. It's something that you need to think about. What's the role of rainwater in water budgeting? So I'll tell you what I think, because I want to be very conservative in my use of water. And I know that landscapes can be designed and managed much more efficiently than they are with regard to water use. So rainwater, that has an effect on the water budget, doesn't it? I mean, yes, the water budget is ETO, and ET is happening when it's not raining. So essentially, ET doesn't really include rainwater. So if we get rain from the sky, could it be that that would offset ETO at least a little bit? And the question about using rainwater in the calculations really is, does it affect the water budget, or does it affect the total water used? And it could, I think it could do both. From a regulatory point of view, which is really where the water budgeting is coming from, I think rainwater should be used to reduce the amount of water that is permitted for a particular place. So if you have a water budget that is 50% or 60% of ETO, and that's going to be your landscape water requirement, you're going to do your landscape water requirement calculations with that. I think that rainwater should reduce that further. It should be more difficult to design a landscape and meet the water budget because rainwater is bringing free water, and it creates an incentive to then utilize rainwater on the water use side of the calculation to offset, right, the water budget. So if we push the water budget down because we're taking rainwater into account, that could be an incentive to utilize rainwater and take areas out of the calculation on the water use side because they're devoted to being irrigated by rainwater, right? So this is kind of a policy discussion more than anything, but be aware that many ordinances regarding water budgeting will take rainwater into effect, and they often do it in two different ways. The first way is they will utilize some percentage of average annual rainfall, and this is, or maybe the previous year's rainfall, and this is called the estimated precipitation, okay, EPPT. And estimated precipitation is often the number that is just in the, in the water budgeting world is 25% of average annual rainfall. And so taking that 25% of average annual rainfall and adjusting the water budget can happen in two different ways. One is even more conservative than the other. The first way, that's less conservative, is it adjusts ETO. So if your ETO is 50 and your 25% of rainfall is 2 inches, let's say, you adjust the ETO down to 48 inches. And you utilize that 48 inches in your calculation of water budgeting. So your ETO has been adjusted first by rainwater, and then it's adjusted by the budget percentage. And that gives you the water budget. That's the less conservative way of doing it. The much more conservative way of doing it, the one we advocate for, is that you calculate the gallons of water that the effective precipitation would give you. So if it was 2 inches, you would calculate on the square footage 2 inches of rainfall times 0.62, and you get the gallons of rainfall. That's how much you're actually, getting from the sky, or you're estimating that you're getting from the sky. Then you do your MAWA calculation, your water budget calculation, as you normally would, using your ETO, and you use your adjustment factor on it, and that gives you X amount of water that is in the budget, and you subtract out the amount of rainfall gallons. So you get your water budget without any adjustment on it, and you subtract out the rainfall gallons. That doubles the rainfall gallons, or not quite doubles, but that gives more rain that you're taking into consideration. Your water budget drops quite low when you do that. But I think that is the even better incentive for having people take sections of their landscape out of irrigation and utilizing rainwater catchment in the soil sponge as the way that area is being irrigated or getting its additional water. So it's a philosophical discussion, but I pretty much guarantee that you're going to see a question about something like that calculate it in one way or another, adjusting the ETO or just taking it out of the MAWA, either way. And at G3, when we do projects, it's worth mentioning that our given water budget that we do all of our projects for is 40%. So we're adjusting the our ETO by 40% to come up with our budget, and then we are taking rainwater out of it. So it's a pretty low number that we are trying to reach. But we think this is the only way that we can really start moving away from potable water in landscapes and even recycled water, because at some point recycled water is going to be potable water too. So we're moving away from utilizing water that it would be drinking water and moving toward really creating incentives for capturing the rain from the sky. That ends water budgeting.